So consider an addition problem like 67 plus 56, and put yourself in the shoes of a student who is doing this for the first time. Now, a student who is just learning the procedure with nothing to support that procedure might make the following mistake. The student might know to add 7 and 6 in the ones column and obtain an answer of 13, and then a student might vaguely remember the next step of the process, which is put a 3 here and put a 1 here. However, if a student just learns a process, again, and no understanding to back it up, they might make the following mistake. They might simply interchange those two digits. Again, clearly a student that makes a mistake like this is not thinking about place value at all. They're just trying to remember the steps of a procedure they were taught. Okay? So this can be a very difficult problem to diagnose for teachers because place value is something that is so ingrained in our heads. We've been using place value automatically for our entire lives. It can be difficult for us as teachers and adults to understand how a student can make a mistake like this. So one exercise that can be useful to put teachers in the shoes of students that are seeing the addition algorithm for the first time is to work in a different place value. Okay? So if we recall from our discussion of place value, the kind of governing rule in our base 10 system is simply that 10 of one denomination is equivalent to 1 of the next higher denomination. When I talk about denominations, I'm referring to the place value denominations, 1 place, 10 place, hundreds place, and so on and so forth. And from this rule, we of course get our base 10 place values. We have the ones place, since 10 ones makes 110. We have the tens place, since 10 tens is 100. We have the hundreds place, and so on and so forth. So what if we were to work in a place value, or a number system different than base 10? What if we were to work, for example, in base 5? What would our governing rule be in base 5? It wouldn't be much different than the governing rule in base 10. The only difference would be instead of 10 of one denomination making 1 of the next higher, we would have 5 of one denomination making 1 of the next higher denomination. So that would be our rule. 5 of one denomination is equivalent to 1 of the next higher denomination. So imagine a number system in which this was our governing rule. We would count in a different way, we would record numbers in a different way, we would add and subtract and do arithmetic in a different way as well. So you can imagine if you, as an adult who are seeing this for the first time, is attempting to do exercises in base 5, you would be in the same shoes as your students who are attempting to do these same exercises in base 10. Maybe the mistakes that you make in base 5 will be equivalent to the mistakes your students will make in base 10, and you can diagnose some of those mistakes a little bit easier. So before we dive into computation in base 5, let's just get our bearings first of all. Let's just try to figure out, kind of like we did in base 10, what are the individual place values going to be in base 5? So let's write out a few slots that will represent the first, let's say, 4 place values in base 5. Now, if we go back to our original discussion of place value, where we talked about someone coming in and dumping a bunch of sticks on the ground and you had to count them, we're still going to need a ones place in base 5, aren't we? Because we still could, again, someone comes in, dumps a bunch of sticks on the ground, and has you count them up. With base 10, we were wrapping them up 10 at a time. In base 5, since our rule is 5 of one denomination makes 1 of the next, we're going to be wrapping them up 5 at a time. But we're still going to have individual sticks on the ground, possibly. So we are going to need a ones place in whatever base we're in. And to figure out the remaining denominations, all we have to refer to is our governing rule of base 5. Our governing rule, again, is that 5 of one denomination makes 1 of the next denomination. So in this case, 5 ones makes 1 of the next denomination. Since 5 ones is equal to 5, the next denomination, the next place value is going to be the 5's place. I know this seems strange, but this is what it is, according to our rule. The next denomination is going to be the 25's place, because 5 fives is 25. Again, our rule is 5 of one denomination is 1 of the next. We're in the 5's place. 5 fives is the same as 25. So our next place value is the 25's place. We can keep going as long as we need to. Let's do one more place value. 5 of one denomination is 1 of the next denomination. 5 25s is the same as 125, so the next place is going to be the 125s place. And again, as we did with base 10, we can keep going as far as we need to. As large as our number is, we can use as many place values as are necessary. So these are the individual place values in base 5. The next thing we can do is we can determine what digits are we allowed to use in recording numbers and adding and subtracting in base 5. And the way that we would figure this out is just go back to base 10. Think about in base 10, what digits are we allowed to use? There is no digit in base 10 for the number 10. Again, the governing rule in base 10 is 10 of one denomination makes one of the next higher denomination. So if you ever have 10 of anything, you don't use an individual symbol to record that. You have 1 of the next higher denomination. Same is going to happen in base 5. If you ever have 5 of anything, you are going to have 1 of the next higher denomination. For that reason, the only digits that we use in base 5 are 0 through 4. So we now kind of have our bearings in base 5. We have our governing rule of base 5. We have the individual place values that we can use. And we also have the digits that we're allowed to use as well. So the next thing we can do is do some arithmetic in base 5. And the first time you see this is going to be difficult because you're used to operating addition and subtraction in base 10. So the first thing we need are, if we're going to do an addition problem, the first thing we need are a couple of base 5 numbers to add. So remember, base 5 numbers only have 0 through 4 as digits. So let's say we wanted to add the digits, or the base 5 numeral with digits 3, 4, 3. And to denote the fact that it's in base 5, I'll put parentheses around it and a subscript of 5. And let's say I wanted to add that to the base 5 numeral with digits 4, 2. Think about how you would add this in base 5. Now, for many people that are seeing this for the first time, it is difficult to add with a normal algorithm in base 5, just because we've never seen this before. So one thing we can do is, again, put ourselves in the shoes of students who are seeing base 10 addition for the first time. How did they learn how to add the addition algorithm in base 10? They learned it through chip models. So we could use a chip model on this problem to show us the steps, the correct steps of the algorithm. So we can draw a quick chip model. You remember our discussion of chip models when we talked about place value in the addition and subtraction algorithm. If we draw a chip model for this problem, again, the only thing that's going to be different is the individual place values. We're not in base 10 anymore, so we're not going to have ones place, tens place, and hundreds place. Instead, we're going to have the ones place, the fives place, and the 25s place. And we know that addition is the act of combining two numbers together to make a sum. In this case, we're adding the base 5 number 3, 4, 3. In expanded form, that means 3 1s, 4 5s, and 3 25s. And the base 5 number with digits 4 and 2. 4 5s and 2 1s. Recall how we would perform this addition with a chip model. All we need to remember is the governing rule of base 5, which says 5 of one denomination makes 1 of the next higher denomination. So in the ones place, we have, if we add 3 and 2, we have 5 1s. But our base 5 rule says that 5 1s is equivalent to 1 5. So as we did in our base 10 chip models, we illustrate combining the 5 1s together, they create 1 5. Right? Well, that's exactly what we do in the algorithm, right? In the algorithm, we would add 3 1s to 2 1s to get 5 1s. We would use the rule of base 5 that says 5 of one denomination makes 1 of the next higher denomination. So we have 5 1s, that is equivalent to 1 5 with 0 1s left over. So that's why we have a 0 in our answer, the 1s place, and we would have a 1, an additional 1 in the 5s place. And we would continue this process throughout until we're finished. Back to the chip model, we originally started with 4 5s and another 4 5s. We obtained another 5, so we have a total of 9 5s now. all we have to do is go back to our governing rule of base 5. 5 of one denomination makes 1 of the next higher denomination. So we can combine 5 of these 5s together to make 125. Over on the algorithm, we do the exact same thing. Originally, we had 4 25s, four 5s, another 4 5s. We got an additional 5 from adding up our 1s for a total of 9 5s. If we have 9 of something, though, we can take 5 of those things and make 1 of the next higher denomination. In this case, we have 9 5s. 5 of those 5s are going to make 125 with 4 5s left over, just as we had in our model. And in the last step, there's no regrouping to do. We started with 3 25s, we obtained an additional 25, and we now have 4 25s. So our answer looks like a strange answer, but this is our answer in base 5, the base 5 numeral with digits 4, 4, and 0. A common mistake to make when we are doing this for the first time is to interchange digits, just like students often do in base 10. So exercises like this can be useful for us as teachers to kind of put ourselves in the shoes of students who are seeing addition and subtraction algorithms for the first time. We can kind of diagnose the types of mistakes that they'll make based on place value.